Okay, so I think I've heard that a lot of people have had posters and discussions about Hafnia. I was not here in the previous poster session and last week, unfortunately. So I know that some of you are already working on this material and already know a lot. But we have been told, okay, keep it simple, start with the basics, and this is what I'm going to do also for those of you who have heard about this material, but they don't know what the secret is. So let's talk about ferroelectric Hafnia. And first, because also I didn't have time in the previous lecture to go into that, I also don't know in which detail you discussed this last week. This week it was not discussed, if I'm correct. Let's talk about ferroelectric memories. So maybe you haven't heard a lot about them because other type of memories are more popular, magnetic memories particularly, but also phase change memories and so on. But maybe for some of you it's a surprise to learn that actually the ferroelectric memories were the first semiconducting memories to be proposed ever, 70 years ago. And it was a PhD thesis of Doodle book at the MIT in so early as 1950. And it's quite obvious that ferroelectrics can be very interesting for memories because of the remanent two states. And this was a cover of the Bell Laboratory records, where they show a barium titanate single crystal, and they electrode it with a crossbar array, and they create 256 bits of memory, already in 1955. So they were taken really seriously already a long time ago. How you make a memory with a ferroelectric? You can use different concepts. You can use, for example, the same concept that is used for DRAM memories, dynamic RAM memories. You have a transistor in series with a capacitor, but in this case, your capacitor contains a ferroelectric material. For example, is a T, and it will look something like this. You have a ferroelectric capacitor in series with your transistor, and then you have some remanence due to the remanence of the ferroelectric, and you can apply pulses to read one state or the other state, to read and write. And the memory window, which is the important parameter for memories, which tell you the contrast between these two states, is larger or is better if the polarization is larger. So you try to create ferroelectrics with large polarization to increase your memory window. But you can also use another concept, which is the ferroelectric FET, in which you use a ferroelectric in the gate, at the gate of the FET. And in this case, the charge that is accumulated at the gate changes the threshold voltage. And depending if the polarization is up or down, your threshold voltage of the transistor will move to the right or to the left. And therefore, for this concept, if you want to increase the memory window, you actually want a material with a large switching field. So depending on what is your material, you may decide that it's better to use one concept or the other concept. Okay, if you want to know more about memories, I highly recommend this paper here, which is really, really nice, by Tony Schenke and collaborators. There is still another concept, and here we have the true experts in the room. That is a ferroelectric tunnel junction. So you use a very thin ferroelectric in between two electrodes that are different. So they have different work functions. And the ferroelectric should be so thin that you can make the electrons tunneling from one electrode to the other. And because of the different work function of the two electrodes, the screening of the polarization will be different in the two electrodes, and therefore you will have a different barrier height if you have the polarization to the left or to the right. And this brings changes in the resistance of the material. And if you have a device in which you can map the polarization state into resistance, it's much more convenient for applications than if you have to work directly with the capacitance, because this rewriting and so on, you have to add every time you read, you delete the state and you have to rewrite it again when this is not the case in this kind. Okay. So ferroelectric memories were interesting. So for many years, the field of ferroelectrics were actually studying how to create smaller and smaller ferroelectrics, because this is what you need to when you want to integrate this in microelectronics. And ferroelectric memories made a lot of headlines. You have, for example, this paper in Science in 1989, where showing all the progress that was done until this moment. They achieved thin films of ferroelectrics that were switchable with thicknesses of 10 to 300 nanometers. That was a record at that time, and very high densities of 2 by 2 microns in cell size. So that was the state at that moment. 10 years later, there was this article in Physics Today showing how interesting ferroelectrics were for non-volatile RAM, a concept that we are still pursuing today, because of the very fast access times, the very good retention, and the very, very good endurance, but especially, and this is where ferroelectrics really excel with respect to other concepts, the very low writing power. So ferroelectric involves very little current, is basically voltage that you need to switch. So if you can achieve switching with relatively small voltages, then the power that is involved in the process is very small. Nevertheless, there were issues, and most of the ferroelectrics that were good enough for this, with large polarization values and so on, were complex structures like perovskites, and they contain nasty elements like were volatile and not desirable in the CMOS processes, like lead or bismuth. So this makes, of course, the whole fabrication process very expensive. You have to create special facilities for that. But also when you do lithography on these materials and you try to get them very small, because the chemistry is complex, then you have edge effects and amorphization and so on. So it was very challenging to get cells below 19 nanometers. So somewhere in 2005 or so, the miniaturization process was kind of stuck, and other type of memories won the race, and people did not hear a lot about ferroelectric memories anymore. In addition to these technological challenges, you have real fundamental challenges also. Because you look at Maxwell equations, they tell us that polarization doesn't like discontinuities. Nature tries to avoid discontinuity of polarization. So if you look at the interface at the ferroelectric, at the interface at the surface, the polarization will find tricks to actually disappear. And for example, creating stripe domains, people from magnetism are very used to that. So you try to create a stripe domain so that the total charge at the surface, at the interface, is 0. Or if you have even dots or smaller objects, then the polarization can actually curl and find all kinds of creative solutions to try to avoid that there is a discontinuity of the polar vector at the interface. So bubbles, vortices, skyrmions, all kinds of things. So if you then try to go to a very small size of ferroelectrics, then most likely you are going to find no net macroscopic polarization that you can switch and use as a memory. And lately, with the very nice developments in microscopy, we can see this very clearly, and we understand that much better than we did in the past. So a little bit more about the depolarization field. So there is a depolarization field in the material that is proportional to the polarization of the material. And if you're able to screen by short circuit conditions your material, so if you put the ferroelectric between 2 electrodes and then you can screen the surface charges with the electrons in the electrode, then you can actually compensate and decrease this depolarization field. The problem is that this is very, very hard to do. You don't have good enough electrodes to actually completely screen the polarization. And this we learned from a very nice work already in 2003 by Junquera and Gosset. And here you see the results of DFT calculations. This is a layer, a very thin layer of barium titanate. Here you can see the barium oxide, titanium oxide, all the layers, sandwiched between 2 electrodes of strontium ruthenate. And you can see here the charge density. And of course, you know that the dipole inside the ferroelectric, the dipoles will compensate, and therefore you will have no charge density, but at the interfaces they will not. The electrode can compensate a little bit the charge, but not completely. In the 2 lines that you see here, dashed and solid, are 2 different values of the polarization of the material, depending on what is the displacement of the titanium. A smaller displacement, larger displacement, you see the associated charge at the interface. And this charge density gives rise to a potential difference, and is small or large depending on the polarization of the material. And this potential difference across the thickness of the material gives rise to the depolarization field. So for very thin films, which is what we want for memories, we have a huge problem with the depolarization field. And this is something that is fundamentally there, and well, we didn't find a solution for that. So because of this, ferroelectric memories have been a niche application. You can find them in the PlayStation, for example. You can find them in identity cards where the memory density that is needed is not huge. Then they are really convenient because they are low power and really good in many respects, but the memory density is an issue. Or was an issue. So that's why it was so surprising when in 2011 there was this paper claiming that hafnia is ferroelectric at the nanoscale. I mean, that hafnia is ferroelectric was already surprising because hafnia was known to be non-polar, but that is ferroelectric at the nanoscale, it was like, no way. So, in fact, they took many years to be able to publish this, about 4 or 5 years, because the referees were saying, no way. And finally, they managed to publish this, and the field of ferroelectrics, the community, really took about 5 years to really be convinced that this was a real effect. It took many other groups in the world to reproduce the same to actually start thinking in that this may be a real effect. So this first paper was published by Uwe Schröder from the NAM labs in Dresden, where they discovered this effect. And the proof that this was ferroelectric polarization was thanks to the group Ulrich Böttcher and the University of Aachen. One interesting thing maybe for you to know is that Rainer Wasser, so the group leader who is actually a very good expert on ferroelectrics, working on ferroelectrics many, many years, was involved actually in these first experiments, and he himself didn't believe it. So that's why he's not actually an author of this paper. So it was really a big shock in the field of ferroelectrics. At the moment, this paper has a very large number of citations and is really followed by a lot of people, and it has been reproduced many times. So let's see what is hafnia and how we can understand the ferroelectricity in hafnia. I have to mention that we don't understand everything yet. So I'm going to, I mean, it's 10 years later and we still don't understand a lot of things. But I'm going to tell you what we understand and what we don't understand. So hafnia is actually a very interesting system, but a bit boring. Or it was a bit boring. This, as an amorphous layer, was actually used since 2005, approximately, in the fabrication of transistors, substituting the silicon oxide. So the dielectric permittivity, so this is K is the dielectric permittivity. The dielectric permittivity of silicon oxide is not that great. So miniaturization was limited by that. And people could go down the 28 nanometers, I believe, node, thanks to substituting silicon oxide by materials that have larger dielectric permittivity, like hafnia. And zirconia is also very close by. Okay? In addition, and this is about amorphous layers of the material, so this is not a ferroelectric. In addition, these materials have a very large band gap, which is different from most ferroelectrics that we are talking about, the perovskites, which have band gaps of about 2.53 electron volts. You can consider semiconductors. These materials are real insulators. Okay? Now, before hafnia was used in transistors as an amorphous layer, as a crystal, it was known simply as a refractory material, not very interesting. So it's very stable at very, very high temperatures. So it was used in high temperature applications. And what was known about the crystal of this hafnia is that the ground state is monoclinic. And then when you increase the temperature, I will show you later, there is a phase transition, but at very high temperatures to a tetragonal phase, and eventually also to a cubic phase, even at higher temperatures. It's also interesting to see that the cubic phase is a fluoride structure. The tetragonal phase is a distortion of this fluoride structure, but the monoclinic phase is actually quite different, with a different coordination. So here you have coordination 8 with the oxygens, and here you have coordination 7. So even though this is the phase transition path, this structure is actually quite different from the others. Okay. So this is something that was done a lot. This is very old work. As I said, this material is used very often for the thermal stability, but the phase transition between the monoclinic and the tetragonal phase in a pure system is actually a martensitic transition. So there's a huge change in volume. And that's not so interesting if you want to go to use it in applications. You want the material to be more stable and not change the volume. So in order to achieve this stability, people actually dope it. And this I believe, I'm not, this is hafnia. So if you dope it with yttrium, for example, then you actually get rid of this change. You actually induce directly the fluoride phase, and you don't have this change of coordination. This also happens with zirconia, and you may have heard a lot about yttrium-stabilized zirconia, which is used as an oxide transport system. And the reason that we don't use pure zirconia but yttrium-stabilized zirconia is precisely the same thing. You want to use this for oxygen transport at high temperatures, and you don't want to have this change of volume half a volume. Okay? And this is what happens when you doped with yttrium. So this is the yttrium-stabilized zirconia that is well known as ionic conductors. And this is what happens when you dope. You create vacancies, and then you avoid this martensitic transition. So a lot of work was done in the past in the crystal structure of these materials in this context of ionic conductivity or refractory materials. Okay? There is, for those of you who are working on this or are interested, I really recommend the papers by Alexandra Navrosky. She is one of my heroes, and she has done a lot of work on hafnia and zirconia nanoparticles, and there is a lot of knowledge on the old papers that she has. So if you compare zirconium 4+ cation and the hafnia 4+ cation, despite they are quite far in the periodic table, they have a very similar size. So whatever we learn from hafnia is more or less true also for zirconia, and I will show later the comparison of the two. Okay. The differences are mainly the transition temperatures are different. The transition temperatures for the martensitic phase transition between the monoclinic and the tetragonal phase is kind of 500 degrees difference between the two of them. And zirconia is easier to form oxygen vacancies, and the surface energies of the two are actually different. So in this first paper, where they reported the ferroelectricity in hafnium oxide, this is the data that they reported. The material had a relatively low thickness, and actually the discovery of this was due to the fact that they were using this in transistors, and somehow they annealed it and crystallized it, which is normally not done. And upon crystallization, they found a peak in the capacitance that is typical peak that people find in ferroelectrics, and then they investigated further. But interesting thing is that this was highly dependent on the doping. So this was silicon-doped hafnia. And you can see here is a clear ferroelectric loop, but then if you dope a little bit more, you get a kind of an antiferroelectric loop that it was not clear if it's really antiferroelectric or this is defect mediated, and so on. And what is interesting is that you seem to need to have a top electrode to cap the material to see this effect. So here you see some X-ray diffraction done on these layers, and you see that it's very different if you have capping with a top electrode or not capping with a top electrode. You have a completely different structure. And they identified the structure that you get in the thin film without capping, like a mixture of these monoclinic and tetragonal phases, which were already known, and none of them are polar. And they identified the structure that they got on the capped layers by a new orthorhombic structure that was polar. These films are very thin, and you know that if you have such a small volume and in thin film form and so on, it's very difficult to actually establish the actual structure. You cannot get a space group and so on with full conviction. You can look at the pattern and say, okay, it is consistent with, but to really prove that this is this space group that is really polar is very, very hard. So there was a lot of work, also theoretical work, trying to see, does it make sense that there is an orthorhombic, a polar space group going around the stability map of this material? And this is actually a publication showing that, okay, you can have non-polar transition paths and polar transition paths. And in the polar paths, there were actually two orthorhombic phases that were polar. And this one, actually, was already observed in nanoparticles. I don't know if I have, yeah, here. So neutron diffraction of nanoparticles of zirconia had actually found patterns that were consistent with two different orthorhombic phases. This was quite old work. They could not distinguish which one was best. So it could actually be this space group or this space group, but this one is actually polar. So the people from Dresden said, okay, yeah, it seems like we have something that is compatible with this, with a polar phase that was ever found in nanoparticles. So this is important, that it's not a stable phase in the bulk material. It was a phase found in nanoparticles. So since that moment, people assumed that the polar phase of hafnia was this orthorhombic phase. There is now much more work done on this. I'm just basically here showing you the first works on that, so the pioneering papers on this. And people indeed showed transmission electron microscopy compatible with this orthorhombic polar phase. So there was quite a lot of agreement. There is quite a lot of agreement that this is the phase that everyone is seeing, and there's by now a lot of papers on that. So if you now look at the original structure of bulk material, so in this case it's zirconia, but hafnia, as I said, the temperatures are different, but the behavior is the same. Then you have this very old work already showing the phase transitions, and this is the martensitic phase transition between the monoclinic phase and the tetragonal phase. These are the ABC lattice parameter, the angle, and this is in red, I signal the volume of the unit cell. So you see there's a huge volume change, which is typical from martensitic phase transitions, and there's a volume reduction of 5% or so. So if you now compare this orthorhombic polar phase with these two phases, it's a kind of intermediate volume. So it's somewhere in between these two phases. And what was interesting, and was shown by the NAMLab group, was that if you want to actually stabilize this orthorhombic phase, you first have to aim to stabilize the tetragonal phase. Because if you stabilize the monoclinic phase to start with, the stability is so deep that you can never get out of it. So the trick to actually achieve this polar phase is to aim to get a tetragonal phase and then change the volume by whatever trick you find to increase it a little bit to be somewhere in between. How to do this? There are a lot of different strategies, and they are all gathered in this very, very, very useful book. If you are working on Hafnia, you really need to get this book. I'm going to mention just a little bit. So you can change the volume by doping, and you can see here different dopants actually help, and you can see the polarization values with respect to the different dopants. And at the end, different dopants work similarly in the sense that they have this kind of parabolic behavior as a function of doping, and they all follow this kind of general trend. And at the end, the idea is that with doping, you introduce oxygen vacancies, and the oxygen vacancies, they change the volume of the material. They change the volume of the unit cell. Now, how to get into this tetragonal phase that I mentioned? So you need to try to get the tetragonal phase, and that's where the size effects are important. And this actually is already known long time ago, also in the works of Alexandra Navrosky on nanoparticles. This is very clearly explained, that if you look at the thermodynamical equilibrium and you add not only the bulk energies but the surface energies, this gamma here, then you can change the stability because of the different surface energies. You can change the stability from the monoclinic phase into the tetragonal phase. So this is a free energy as a function of the molar surface. Here are the large particles or single crystals. As you move here, the crystal size decreases. So beyond certain crystal size of about 30 nanometers, you actually can stabilize the tetragonal phase. So you don't need to go to high temperatures or high pressures or wherever. Size reduction helps you to stabilize the tetragonal phase. And that's why this phase is available in thin films, but is not available in the bulk material, or more difficult to find. I don't know if you work on nanoparticles, but you may know that the effect on a nanoparticle, the material inside the nanoparticle experiences a kind of pressure due to the surface energy. The larger the surface energy, the larger the internal pressure in the nanoparticle, and the smaller the radius, the larger the internal pressure on the nanoparticle. So you can actually sometimes predict which phase you're going to find inside your nanoparticle by looking at the pressure phase diagram of Hafnia. Okay, and indeed, in the pressure diagram of Hafnia in the old papers, you find orthorhombic phases also at high pressure. So the idea is, as I said, go to grains small enough to stabilize the tetragonal phase, then do some doping, some strain, some electric field, whatever, to increase a little bit the volume to hope that you fall in the stability of this intermediate phase. So this is Alexandra Navrosky, and she has, as I said, a lot of work on what happens when you change the nanoparticle size. And you indeed, by changing the nanoparticle size, you can stabilize the tetragonal phase, but if you change even further, you decrease the nanoparticle size, you even can stabilize the cubic phase. So for small enough particles, the cubic phase could be the stable phase. So this is the work that was done, as I show you. Another interesting thing is the composition. There was a lot of theory work done on, what is the stability map of this. And you can see here energies for pure Hafnia as a function of the size of the particle, so including the surface energy in the Gibbs energy. Then you can see that the ferroelectric phase, so these are the monoclinic, tetragonal, cubic phase in different colors, and the ferroelectric phase is in red. So you can see in pure Hafnia, if you want to stabilize the ferroelectric phase, you have to go to particles that are about 4 nanometers in size, really small. Then, if you go to pure zirconia, you, in principle, cannot stabilize the ferroelectric phase. So you can, but you can very easily stabilize the tetragonal phase, which is actually something that we wanted. We wanted to stabilize the tetragonal phase to make sure we don't fall into the monoclinic phase. So if you actually use pure zirconia, you easier are out of danger, not stabilizing the monoclinic phase, but to stabilize the ferroelectric phase, then you need an extra step. Okay? So a very interesting sweet spot is mixing these two things, like half hafnia, half zirconia. You actually get a stabilization of the ferroelectric phase straight away, but the size of the particles are actually larger, which is easier. Okay, that's why a lot of people, including us, are using these compositions. And yes. Actually, no, this is a very good question, but we don't understand the origin of polarization. So, no, there is a very big change in polarization with any doping, but it also depends a lot on the oxygen content, and it's very, very hard to predict. Yeah, that's a very good question. Okay, so among the paths to ferroelectricity, you can also get applied ferroelectric electric field. For example, if you stabilize this tetragonal phase, the tetragonal phase is actually antipolar, or some people say it is anti-ferroelectric. From the point of view of the theory, it's antipolar. So you can actually apply an electric field to this tetragonal phase and induce the polar phase with the field. You can also use a combination of a strain and electric field to stabilize the polar phase. And in this paper, for example, they claim that here no size effects are considered, so they don't include any surface energy in these calculations. So there are many different strategies that you can actually use to stabilize the polar phase, but the general principle is to get something intermediate between the tetragonal phase and the orthorhombic phase, avoiding the monoclinic phase, avoiding the monoclinic phase. Okay? These strategies are actually consistent with the fact, I didn't mention yet, that in the ferroelectricity of this material we have what is called the wake-up effect. This is something we didn't hear before hafnia. In classical ferroelectrics, no one was talking about wake-up effect. I mean, you knew in ferroelectrics, you know that the first cycle is always weird. So you make a first cycle, the second cycle, but it's normal, the dipoles need to rearrange. But then after the third cycle, you just get the same polarization. And then you look at the fatigue, and then the fatigue of the material requires 10 to the 6th cycles or whatever. But here there is really what is called a wake-up effect, which is unique of hafnia, which means sometimes you need 1,000 cycles or 10,000 cycles to actually see the polarization rising. So the material at the beginning is really different from the material after cycling. And this can be explained by these effects, the fact that you can actually change the stability by applying an electric field or by straining the material. And you can see here the typical examples of wake-up effects. This case is already very good that the material starts with certain polarization, but very often you have something like this, like really strange loops with double peaks and so on, which look pinch in the origin, and then you really need a lot of cycles to wake the polarization up. And this is already a very optimized situation. In many cases, you start just with no polarization. Okay. With time, people have learned, because of these strategies, to actually be able, and using quenching and kinetic effects, to actually stabilize films that are not so thin, because, as I said, there is a way around it. So for example, this was one of the first papers that showed relatively thick layers that were ferroelectric, and that was already quite surprising. These thicknesses were already quite unexpected, but so it's possible. In this case, though, when actually this is not in the paper, but I contacted the authors and they sent me this picture. So indeed, the layers are thick, but the grains are still very small. So in this case, actually, the thermal quenching and the thermal treatment they use took care that the grains themselves were still quite small. Nevertheless, in more recent years, people have actually managed, and I think most of the work and a lot of the work in this direction has been done by the group of Funakubo in Japan. They now manage to grow very thick films and without these small grains. So it is possible, and actually the group in Rutgers, they have managed to even grow a bulk single crystal. It's tiny, and they only managed so far with this doping, yttrium-doped hafnia, but they have achieved, by thermal quenching in particular ways, the same strategy, aim to grow this tetragonal phase and then quench it so that it gets into this polar phase. So I'm going to wrap up this introduction part. How long I'm talking now? I still have like 20 minutes, right? So this is more like the introduction part, and I want to wrap up. So finally, we have a material that is actually ferroelectric at the nanoscale. It's already integrated in microelectronics, so it's great. There's no issue with the chemistry of this material. The ferroelectric polar phase is the so-called orthorhombic phase. It's intermediate between the monoclinic phase and the tetragonal phase that are well-known phases in these materials. And you can stabilize it by lowering the grain size, increasing the pressure, changing the composition, and so on. There are several strategies. And stabilizing this orthorhombic phase is only possible starting from the tetragonal phase. So you should avoid to fall in the stability of the monoclinic phase. This composition seems to be a kind of an ideal compromise, but actually a lot of people are working on other dopants like yttrium, lanthanum, and indeed sometimes the polarization can be increased by other dopants. So this is nice, but it brings a lot of open questions. One is why it does not depolarize. So we still have, we understand that there is a polar phase at the nanoscale. Fine. Now we believe it. But why it does not depolarize? Maxwell equations should still apply to this, right? So how does the material manage to keep the polarization at the nanoscale without creating vortices or any other structures? Still a big open question. We don't know the answer. Now, other things you want to know in the case of ferroelectrics is what is the paraelectric phase. You learn a lot about the nature of the ferroelectric phase by understanding the paraelectric phase, and then how you actually create a dipole. Is it a soft mode? What it is? And yeah, there is very little known about the paraelectric phase in this material. There are now a couple of papers on it, but there is a lot of controversy. Some people think it's a soft mode, some people think it's not. So not clear at all yet. What is the maximum polarization that can be achieved? Like Andreas asked, is also not so clear because we don't understand the nature fully. So for this, we thought, okay, we need to study single phase samples because all the samples that people are typically reporting are grown by ALD because they were grown, the same procedures that they were using to integrate in transistors, the ALD process. They create a polycrystalline film and then they anneal it to crystallize it to get this orthorhombic phase. So what you get at the end is a polycrystal, and actually is very hard to get in that way single phase because you may get still a part of the tetragonal phase still in the film, which is not polar. You may induce the monoclinic phase, which is the ground state. Part of the film may be monoclinic. It's also not polar. So when you get a specific value of polarization, it may be that the part that is polar in your film is just a small percentage of the total volume. So in order to understand what is going on, it's interesting to make sure you grow single phase samples, and if you could get them perfectly oriented and texture and so on would be better. That's why we decided to do pulse laser deposition of this material to understand better what is happening. So we started to grow on different substrates trying to get epitaxial films, and in the meantime some work appeared in the literature, again from the group of Funakubo, and these were the first epitaxial films that were reported in hafnia. They were hafnia, yttria-stabilized, yttria-doped hafnia on yttria-stabilized zirconia. So, you can buy substrates, single crystals of yttria-stabilized zirconia, and therefore it's a fluoride phase grown on another fluoride phase, and it grows very nicely. epitaxial. And in this case, they could get very large polarization. It was a record polarization of 40 microcoulombs a square centimeter, which is similar to what one can get in perovskite materials. Because of this very good quality of the epitaxial films, they also grow them by pulse laser deposition. They could actually follow one of the structural peaks that disappeared at about 400 Celsius, and actually it looks like a phase transition, like what you expect for a phase transition. So this is one of the few papers that show a phase transition in ferroelectric hafnia, happening around 450. A lot of people have tried to reproduce this. There are a couple of papers, mainly by them, showing phase transitions on hafnia. There is a paper by the hafnia group showing dielectric measurements of the phase transition in yttria-doped hafnia, showing a peak in the dielectric permittivity. Sorry, I didn't put it here. But a lot of people I talked to, they don't find a phase transition, including us. So it's not so easy to actually get material that shows a phase transition. But there are examples in the literature. Okay, so we started growing on different substrates, but to our surprise, we found the most epitaxial films to grow on a perovskite. So we work, of course, very often with this material because we work on perovskites, and we were actually motivated, I will explain later, to use this buffer layer particularly, and we were very nicely surprised to see that we could actually grow hafnia zirconium oxide epitaxially on a perovskite. And you can see here, this is the STO peak, the LSMO peak with the fringes, and here you have a hafnia layer. This is a very thin 1.5 nanometer hafnia. And when you go to 3 nanometers, 4 nanometers, you see the strain is released very, very quickly. So you grow, actually, the very thin films, you grow under enormous amount of strain. And then the strain releases, and if you keep on growing thicker and thicker, this is from 4 nanometers here up to 27 nanometers, then this actually does not relax so much more anymore. You see the monoclinic peak starts appearing somewhere. So this means if you grow thicker, you actually start stabilizing the monoclinic phase, which is not polar. So if you want to get the maximum polarization, you need to stay quite thin, because otherwise you start getting non-polar phases. Okay? So what is interesting is that even in the fully relaxed films at 27 nanometers or something like this, the peak that we found, that we thought it was our fully relaxed peak, is still not exactly at the position where the people growing by ALD on polycrystalline samples found their orthorhombic peak. So we did more detailed analysis, pole figures, and so on, and we saw all these different poles. So this is the 111 peak out of the plane, and then you look at the other 111 peaks, and you see 12 poles, which means you expect 3 from the other 111 peak. So you see 12 poles. This means you have 4 different domains, which corresponds to the 4-fold symmetry of the substrate. And this is indeed what we found. Sorry, I didn't. I signaled the different domains by the same color. So you have 3 peaks of one domain, and then 3 other peaks of another domain, and so on. And then what is interesting to see is that if you actually look at the 2 theta position of all these peaks, you see that you have actually 1 to 3 multiplicity. So you have the out-of-plane 111 peaks is actually different, has a longer lattice spacing than the in-plane ones. And if you look at this 1 to 3 multiplicity, the only symmetry that actually fits with that is the rhombohedral symmetry. If you have an orthorhombic unit cell, this is not what you expect. So we thought, okay, this is a different, I mean, your peak is different, your symmetry is different, so we reported a rhombohedral phase in this material. The way we saw this is, okay, how we could actually stabilize a rhombohedral phase, certainly not from a tetragonal phase under strain. There's no way you can imagine that if you start with a tetragonal phase and then you strain it in some way, you can actually get a perfect rhombohedral phase. So the model that we have in mind is that if you actually stabilize the cubic phase, which was allowed by Alessandra Nabrowski, so what she has reported and is known that if you actually decrease the size even further, you stabilize the cubic fluoride phase. So if during the growth you actually start with a cubic fluoride phase and this cubic phase is under strain, then you can actually elongate the out-of-plane direction and induce a rhombohedral symmetry. Oops. Okay. Actually, these rhombohedral phases are predicted by the theory. It is possible to stabilize a rhombohedral phase, but it's higher in energy than the orthorhombic phase, actually. So it's not impossible. And what is interesting is that the very thin films had a very nice polarization, quite high. We didn't need any wake-up cycling. This is very good for applications if you don't have to do all this cycling. And what is interesting is that for the rest, the behavior is very similar to what everyone else is reporting for the orthorhombic phase. So if you grow thicker, you get more of this monoclinic phase, you reduce your polarization quite drastically, like everyone else is also finding. So if you look more carefully how this epitaxy is happening, you see that there is something going at the interface, a layer that seems to be rich in oxygen vacancies that is helping this epitaxy between the LSMO layer and the Hafnia layer. As I said before, this Hafnia has a very large band gap, so we thought, okay, since we already have the LSMO layer, and actually that was our plan from the beginning, this could be very interesting for tunnel junctions, because tunnel junctions suffer from leakage quite a lot, and this material seemed like a very good candidate for that. How much time I have here? Not so much. So I think you know more or less about tunnel junctions. You have, originally the concept of magnetic tunnel junctions was put forward. You know, you have a very thin insulator between two electrodes that are ferromagnetic, and one of them can, the magnetization can be switched. So you can have the tunneling magnetoresistance effect and change the resistance. So this is the basis of magnetic memories. The concept of ferroelectric tunnel junctions implies that you have now two different metals, and as I said, a ferroelectric barrier, and by changing the magnitude of the polarization, you can change the resistance. So this is called the tunneling electroresistance effect. And you can have now the two effects combined, and here we have Manuel and collaborators were at the birth of this concept. You can combine these two effects. You have a ferroelectric between two magnetic layers, electrodes, and then you can change both the magnetization of the electrodes with a magnetic field and the polarization of the ferroelectric with an electric field, and have 4 different states of memory. This is done so far and demonstrated with barium titanate and lead titanate and other perovskite materials, but the problem has been always the leakage, and it is very difficult to get standalone devices with these materials due to the leakage. So in Hafnia, we shouldn't have that problem, or much less, and indeed, when we make devices, these devices were made with by Sylvia Madsen and her group in Paris. Very beautiful devices. Here you see the Hafnia layer, which is only 1.5 nanometers. And you see this material is is such a good insulator that if you actually use a 3 nanometer barrier, you already don't have any current. So this is actually quite interesting. And we could make devices that are 30 by 30 microns, actually. This is, and they still function perfectly and without leakage, wire bonded, and so on. So that's actually quite nice. If you look at the tunnel electroresistance effect, you see a 400% change, 4 times larger, depending on the direction of the polarization. And if you do also magnetic field dependence, you see these 4 states that you expect from this material. So that's actually very nice. But if you actually put these 2 plus 1 on top of each other, you see that they are basically the same, which means that there is no magnetoelectric coupling actually in the system between the ferroelectric layer and the LSMO layers, which is a bit disappointing and actually strange because you expect kind of coupling at the interface or so. Nevertheless, when we did electric field cycling, we found a lot of differences, and I'm not going to go into the magnetic data because I have no time, but we see a lot of difference, and we actually increase the tunnel electroresistance effect by 4 orders of magnitude by just cycling the material. Unfortunately, this still needs to be optimized, and at some point after 1,000 or 10,000 cycles, the junction breaks completely. But we try to understand how is this, why we are increasing the tunnel electroresistance effect, which is so interesting, and can we actually control it better? And for that we needed to understand what is going on. And that was done with the help of the group of Bart Kooi, the microscopy lab at the University of Groningen, and Pavan Nukala, who is an expert in microscopy and was in my group at that time. So it's interesting when we look at, we had the full device with the LSMO electrode, STO, LSMO, the Hafnia, and Cobalt and LSMO, different devices inside the TM, and we apply electric field in situ, in operando, so that we see what is happening while running the cycles. So if you focus only on the bottom electrode, this is the LSMO bottom electrode, you see that depending on the electric field that you apply to the top electrode, you actually get a phase change, one of these topotactic phase transitions between the perovskite phase and the Brown-Millerite phase of LSMO. And this is actually reversible. And this was a big surprise to us. And this Brown-Millerite phase has a layer that is rich in oxygen vacancies, so actually the oxygen has to go somewhere in the material. And indeed, because we are using this technique, this integrated differential phase contrast STM, you are actually able to detect also oxygens, which is very important for Hafnia because the polarization of Hafnia actually has to do with the shift of the oxygen ions rather than the cations. So we actually could look into the layer of Hafnia actually and see that the oxygen is migrating from the bottom electrode to the top electrode and back when you apply the reverse voltage. So it is clear that what we are seeing is actually oxygen moving across the Hafnia layer between the electrodes. Was also interesting to look carefully at the Hafnia layer. Indeed, show that the samples that we have are consistent with the rhombohedral symmetry, but also to realize that if you actually look at the polarization, you can see the oxygens and the Hafnia, you look at the, try to extract the polarization value, is actually very small. While in the experiments, we are seeing polarizations of 30 microcoulomb square centimeters. So something doesn't add up, and this is one of the open questions that we actually have. What is actually the polarization? So it's a big, big question. What we saw in the TM was actually consistent with resistance measurements we had done in the whole stack, which basically reflect what is happening at the LSMO. So if you are familiar with LSMO, the LSMO has a metal to insulator transition about room temperature, this LSMO with this particular composition. But if you have oxygen vacancies, it's well known that with oxygen vacancies, the transition temperature shifts to low temperatures. So here we see that depending on the cycling, at the beginning our LSMO has relatively a small amount of oxygen vacancies, and after cycling, the transition temperature moves to low temperatures, indicating indeed the Brown-Millerite phase is actually appearing. Also, the difference between the polarization up and polarization down of the ferroelectric also shows the same shift, indicating that depending on the direction of the bias that you are applying, you have either the Brown-Millerite phase or the perovskite phase. Okay? So this should be quite interesting for what we discussed the other day, to use these materials for neuromorphic devices, because you have, in principle, you can have a polarization that you switch in a quite fast, because it's about local dipoles, unit cell level dipoles, balancing somehow with the oxygen vacancies that are moving quite slow, So you have two time constants and different dynamics of different processes, which is what we actually needed to create this hysteretic behavior, if you remember. So it seems like these materials could be very interesting for memristive applications. I think it's already a bit late. I have some slides showing that indeed hafnia shows this kind of potentiation and depression that you can get with pulsing. This is work done by Infem Wei when she was in my group. And it's very interesting. So depending on the pulses that you apply, you can increase the polarization or decrease the polarization. You can tune these pulses to be different, with different widths or with different magnitudes to change this increase and decrease to control it. What we find very interesting about this is that if you compare what we got with our rhombohedral epitaxial fully oriented hafnia, and you compare it with people have got on polycrystalline orthorhombic ALD grown non-oriented hafnia, is very similar. So there is also in ferroelectrics you don't expect this. The symmetry of the material is everything. If you change the symmetry, the polarization changes completely. You don't expect to have anything similar. What happens in hafnia? Why? Why we see different symmetries and the properties are so similar? It's actually another big question we have. So conclusions. One can get multiferroic tunnel junctions that can be fabricated as stand-alone, which was not possible in other ferroelectrics. They show 4 resistance states with very good uniformity and device-to-device reproducibility. The cycling is still an issue. You cannot cycle for many, so reliability is actually an issue still that we need to work on. You can get 4 orders of magnitude enhancement of the tunnel electrode resistance in these materials, and operando measurements in the and also resistance measurements shows that there is oxygen migrating through the layers. And this interplay between electronic and ionic effects make them very interesting for synaptic or neuromorphic devices. And maybe this is also the key, this balance and the interplay with the oxygen vacancies, which are positively charged, by the way, in this material, maybe the explanation why the polarization can survive at the nanoscale. Maybe the oxygen vacancies are so efficient screening this polarization that the polarization doesn't need to find any other way to be screened, and we can actually get this. But all these are still open questions. Okay? So with this, I just thank you and questions.